and one is A, one is B, over magnitude A, magnitude B. So that's, let's see, I plus, I did the curve first, didn't I? So I plus 12J, dotted with I plus 4J. I'm dividing by the magnitudes, square root of, let's see, 12 squared, ooh, gross, 144, 145, and the square root of 17. 17 is getting in there a lot. So, what's the dot product?
I believe it's 49.
I believe you're right. And, and I'd like to actually work the thing out this time. So go ahead and calculate that, that cosine for me. I forgot to bring my calculator.
I got 9.3 degrees.
I think you're right. I think I remember that one. 9.3 degrees. Let's see. So the cosine of theta is this, and theta is 9.3 degrees. Now, I want to do this one a different way. In 2 dimensions, there's almost always an easier way than to go to the dot product thing. And by the way, first of all, let's get this other one here. Let's get this fatter angle first. So for the curve, let me just for the curve, now I'm going to want r prime of what? To get this vector right there. Up here, I substituted t equals 2. What do I substitute down here? Here I have r prime of 2. R prime of what? When I want to do the other intersection.
0.
0. X is 0, y is 0, and t is 0. And so let's see, that goes in here. I've got I plus 3 times 0 squared, j. Oh, so that's just the vector I. I drew my vector I a little bit too long. That looks more like 2I, but anyway, because this was 2 right here. So here's vector I. Maybe we'll call this vector V. I've already used A and B. So we have V and W. And for W, I'm going to take, well, F prime at 0. What's F prime at 0?
Same thing.
Same thing?
I was
So I can record it. Alright. Now I guess we could still call it B if we wanted to. Alright. So let's work this one through. I've got the cosine of this other angle, which I'll call phi. Cosine phi will be V dot W over magnitude V magnitude W. What's V dot W?
1.
1. So 1, and then this other one would be a 0 times 4. And magnitude of V?
1.
1. Magnitude of W?
Square root of 17.
Square root of 17. So go ahead and calculate the arc cosine of, of 1 over root 17 for me.
So 76 degrees.
Okay. 0.0, I think, wasn't it?
Yes, sir.
I usually ask for nearest tenth, so if it turns out to be, if the nearest tenth gives me the whole number of degrees, I usually go ahead and put the 0 in there. All right. Now let me show you the easy way. I'm going to start with the second one. I'm going to start with the one at the origin. I'm going to remind you of some trig. Maybe you had it in pre-cal or wherever. But, well, not necessarily. Here we go. What if I have some curve here? Here's my tangent line. Let's say this point here is A. So if I wanted the slope of this thing, what would that be in terms of calculus? And this is F. F prime. F prime of
A.
Okay. And then here's this angle. We just want to do an angle with the horizontal. See over there at that origin, the angle at the origin would be like that. So it's the horizontal. And so if I want this angle with the horizontal, running out of angle names, how about alpha? Well, not A. Mu. We'll call it mu. Well, I could call it P or pi, but then I'd get mixed up. I think it was 180 degrees. All right, so anyway, how are M and mu related? How are M and, I'll call it theta. How are M and theta related?
Triangle.
So if I go over 1 and up M, or if I went over delta x and up delta y over delta x is what?
Rise over.
Yes. And what else is it?
M.
And in what else is it?
Slope.
What is it in terms of the angle?
In terms of the.
Oh, it's tangent.
It's tangent. So, for that straight line, and notice, the other vector is horizontal, so all I really need to know is this thing, and its tangent is the slope. What's the slope over there?
Slope
On the straight line, what's the slope? 4. All right, so I'm going to do the tangent of theta equals 4, and so the arctangent of 4 76.0. And that's a lot easier than thinking about all that vector stuff. How can I predict that it comes out the same? I can think of a couple of ways. For one thing, it is the same angle, so it better come out the same. But what, look under the hood. Why did they come out the same? And the answer would have to be trig identities. So think about that a minute. Here's 4. Here's 1. What's this hypotenuse here?
Square root of 17.
Square root of 17. So when I do the arc cosine of 1 over root 17, I'm getting my angle. Nothing to it. All right? 2-dimensional angles are easier than 3-dimensional angles. Now let's do this angle up there. It's not quite as easy as this one, but it's close. What do I have to do? Look at this thing sideways and think of that as horizontal? No. I'm just going to draw a horizontal. And I just find this angle and subtract this other angle. Well, what is this angle?
76.
76, okay. And so I've got to subtract 76 from this larger angle. And so we're going to go over 1 and up the slope. All right? So what's the slope? Let's see, I've got y equals x cubed. To find the slope of a tangent line, derivative, okay. So let's see, dy dx is 3x squared. And at that point, the m would be dy dx evaluated at what x coordinate? 2. So I get 12. And so the arctangent of 12 equals, I bet it's going to be somewhere around 85 degrees.
Yeah. I was gonna wait for you to say it.
Would you think it would be 85.3?
85.23.
Ah, so there's a round off error going on. Okay, well, 85 point something. Give me a few more decimal places. 2, 3, 6, that'll be enough. All right, and then the arctangent of 4 was 76, or actually 76.9 something, right?
75.9.
I mean 75, yeah, 75.964.
64.
So when I subtract those, let's see, 2 and 7 and 2 and 9. Yeah, that's it. And so I round it to one decimal place and I get 9.3 degrees.
And I didn't see
So anyway, I thought I'd just do a little excursion in some of the geometric aspects of calculus that you usually don't see a whole lot of. But this idea that the slope is the same as the tangent of the angle, I mean, that's kind of key to a lot of stuff. But it doesn't help in 3 dimensions, because as these curves twist around,
Yeah.
I mean, then the plane, the plane that they're in kind of also twists around. Well, anyway, so supplement 2.5 gives you a lot more angles to find. Some of them in 2 dimensions, some of them in 3 dimensions. One of them in 4 dimensions. So problem 2 says find the angle between 1 comma root 2 comma 2 comma 2 root 2. That's 4 numbers, and this other 4 numbers would be. And all I'm telling you is the dot product and angle work the same in 4 dimensions. So how do you visualize it? You don't. But you can still work out that angle. And the answer for that, when you get it, it's the same angle that you got on supplement 1 in one of those problems with the big old cube. And then the next problem says look at the sine function and the cosine function, and look at where they intersect. And here's the one that's closest to the origins. And they make an acute angle, and they make an obtuse angle. And I wanted to know what's the obtuse angle. And again, if you want to use all the vector stuff and the parameterized curve stuff, then you need to parameterize this one that way and parameterize the other one backwards. Oh, how's that going to work? Well, even if you do the vector stuff, just go forwards, calculate the acute angle, and then how do you get the obtuse angle?
Subtract it from 180.
Subtract it from 180. That's what I did. But you can also do all this tangent. Tangent? I thought this was sine and cosine. No, I can do the tangents of these angles. All right. And again, you'll recognize the angle that you get if you've already calculated through some of these other things. All right, well, anyway, I'm gonna let it go with that and move on to the next chapter. But again, I'm trying to give the impression, whether it's justified or not, the impression that we can calculate anything we want. All right, so the next chapter we've got functions of several variables. Real valued function of 2 variables, real valued function of 3 variables, as opposed to what we had over here, which was a vector valued function of 1 real variable. So either we think of there being just 1 vector for the output, or we think of there as being 2 or 3 numbers for outputs. But now we're switching over. We're looking at things like f of x, y, z, or f of x, y, or that kind of thing. And I asked you to read the first 2 sections of this. So I believe in the other book it was the first 3 sections before they got to any calculus. But let me just, okay, limits and continuity is 13.2. Partial derivatives is section 3. That's what I want to get at. But section 1 has a lot of pictures, and I've already drawn a picture of a function of 2 variables. This was my sort of favorite example here, f of x, y, the circular parabola. Z is f of x, y. And when you're going to draw a graph, you need another variable, another dimension to let it curve into. So abstractly, we've got f of x, y. And when I want to see the picture, I've got z equals f of x, y. Abstractly up here, I've got f of x, y, z. If I wanted to see the picture, I'd have to twist my head in 4 dimensions and get w equals f of x, y, z. So anyway. Here's what we're going to do for derivatives. Where derivatives come from in Calculus 1, they came from slopes of tangent lines. And I'm going to do the same kind of thing here. Let's not worry about f of x, y, z right now. I'm going to worry about f of x, y. The ones that I really can draw pictures of. Well, not very well maybe. But. So you're going to see this picture a whole lot. And I don't mean just tonight, I mean throughout the semester. So I'm going to draw the surface. And of course it might go to infinity in every direction or whatever, but I'm just going to draw a part of it as usual. Because I couldn't draw it all if I wanted to. Now, let's see. In Calculus 1, we talk about tangent line. And in order to get the motivation for the derivative, what we did is I want to figure out the formula for the tangent line by sneaking up on it. I'll draw a chord, a secant line as it's called. And then, or I could draw the secant line over here, which, considering how steep that was, it might have been better to draw it over here. But anyway, so the true tangent line is trapped in between this one and that one. And I can take a limit of the slope of the secant line from the right or from the left and get to that intermediate, that tangent line. And so what we do, and I've already gotten to where I think I could draw a better picture. And of course, you've seen this in the book in any number of pictures. So we have delta x. And now remind me, does this book use delta x or does it use h? It uses, I see a bunch of delta x's on page 893. What did it use in calculus 1?
Either that or dx or what?
Or dx, yeah. Yeah. So there in the delta x dx. Good, I like that. All right. So here's delta x. Or we have this bigger delta x, but now we're just letting it go down to 0. And we take a limit of delta y over delta x, as delta x goes to 0. And let's see, so here would be delta x, and then this would be delta y. And that gives me a slope. And in the limit, I get down to this one, the m, which would be, and you mentioned dy over dx, also known as f prime of x, if this is x up here. And so this limit gives me dy dx. And it's also known as f prime of x. So all that stuff there. Now, with surfaces, right away I got some problems. By the way, I printed these out and I didn't actually hand them out. Some of you won't need these, but hand those out. To anybody that needs them, some people don't need them. So, find some point in here. And underneath will be xy, and we're doing z equals f of xy. And then the problem here is that there are, on a surface, even if I pin down one point, there are lots of tangent lines, okay? In fact, later on I'm going to be talking about the tangent plane. All the tangent lines together make the tangent plane, okay? So if I'm going to do the slope of a tangent line, I have to say, well, which tangent line? Towards the middle of chapter 13, is that what this is? Towards the middle of chapter 13, they're going to talk about all these other tangent lines, but in this section, they're only talking about 2 of them. The one parallel to the xz plane, and the one parallel to the yz plane. And it's easier to draw the pictures for the one parallel to the yz plane. So that's what I'm going to do. I'm going to think of I guess I should get one of those pages over there, but I'm going to think of cutting through this thing, and that will give me some curve. So if I take this value of x, then I will get a curve like that. And I'm then going to do the sneaking up process like I did over there. So I'll go to this other point on the curve. This will be a secant line, a chord. And let's see. I guess this will be delta y. This is delta z. And so this slope for this line is going to be delta z over delta y. And I'm going to take the limit as delta y goes to 0. And of course, it looks like I'm doing a right-handed limit, but I could just as well be doing the left-handed limit, and it sneaks up on from both directions. Sometimes you get different answers from the left and the right, but we're not going to worry about that right now. In fact, we're not gonna worry about that much at all. We're gonna mostly stick with the nice functions here. So anyhow, I want the limit of delta z over delta y instead of delta y over delta x. Y and x are both independent variables, so those increments belong on the bottom. And I'm going to take the limit as delta y goes to 0. And, yeah. And that then is our derivative. And there are several notations for this. I'm going to start out with the notation using capital D. So the derivative of f, where? At xy. And now, that's as opposed to doing this tangent line over here along this way, or some other one in one of these other weird directions. So I have to distinguish this one from all the rest of them. And so I'm going to use a y for that. That's the derivative in the y direction. The derivative with respect to y. I will mention some of the other notations. Sometimes we put the subscript on the function name. So f sub y of xy means absolutely the same thing. Relatively the same thing. And then there's this notation. Del f del y. And then you can put the xy declaration out here if you want to. I usually don't bother with it. There's so much writing in Cal 3 that I tend to do a lot of abbreviating, and so does everybody else. Anyway, so this thing, how do we do delta z? Well, how do we do delta y back over here? We subtracted the function value out here from the function value over there. So delta y was, let's see, this was x here, so that was f of x subtracted from f of x plus delta x. That's how it works. It works the same here. This is f of xy. And what's this other one?
F of x comma y plus delta y.
F of x comma y plus delta y. We're only changing one coordinate at a time. All right? So when I want to do the x partial derivative, I'm changing x. Delta x will be non-zero, but delta y would be 0. And here, delta y is non-zero, but delta x is 0. So we keep the x constant, and that's the key to doing the computations. All right, now, as I recall, I kind of did an example last time, didn't I? Right at the end of the class?
I don't think you did.
Just me.
What?
I think I asked you a question.
Oh, just for you, okay. Yeah, he had his own class afterwards. So I guess I should do a computation. So let's take a particular example. And of course, if I wanted d sub x f at xy, or f sub x, or del f del x, then this would be a limit as delta x goes to 0.
F of x plus delta x comma y
Mm-hmm.
minus f of x comma y all over delta x.
And that would be the line that's perpendicular to the one that we were doing before on the graph.
Well, it would be the line that's in this plane as opposed to the line that's in that plane, but they're not perpendicular necessarily. the horizontal ones would be perpendicular, but this is slanted up and that's slanted up, so that's fine. But yeah, they are in perpendicular planes. All right, so let's take an example. F of xy. Let's not get too awful. I'm gonna take an x cubed. That's not really too awful. And I'm gonna take maybe plus 5 x squared y squared. That won't be too awful. And I want to calculate both d sub y, f of xy, and d sub x, f of xy. I could first just do one where it's all constants. I could take d sub y, f of 3 comma 4 or something like that. But we're not going to get that up close and personal with all these limits, so I'm just going to do the generic example. But anyhow, so I'm going to take a limit, delta y to 0, and I'm not going to write this down again, but that's what we're after, right? So f of xy is this. Don't forget the parentheses. And then here, we're going to have x cubed plus 5x squared times y plus delta y squared. And I don't guess we need parentheses there, but anyway, delta y. And it's a polynomial, for goodness sake. I mean, this can't be that bad. So I just multiply it out. Notice first, the x cubes cancel. The derivative of the x cubed part is going to be 0, because as far as the y is concerned, x cubed is what?
Constant.
Irrelevant, yes, but what was it?
Constant.
Constant, okay. And therefore irrelevant. It's not irrelevant, it's in the problem. So 5x squared y squared. I'm going to skip a step here. We're going to get 2y delta y times the 5x squared. So 2 times 5, we're going to get a 10 x squared y delta y. We're going to have a 5x squared delta y squared. And